So good evening, everyone. So it's in the very spirit of the programs here at Institut Henri Poincaré to propose broad audience presentations besides the more specialized talks, and the idea is to give an access to mathematical science to our ultimate sponsors, that is the people in the street interested in science. So it's we have two such conferences planned during this PRACQSYS meeting. So one today and one tomorrow, and it's my great pleasure to introduce today's lecture given by Klaus Mølmer and Kim Helweg. So just a few words before letting them talk. So about Klaus first. So he's for those who don't know him, he's a theorist specialized in quantum mechanics. So he's famous for his works on the dynamics of quantum systems. His works in quantum optics, quantum atomic physics, and quantum information. He's also very much involved in science popularization in the most noble sense of it, and I can testify of the success of his lectures in Aarhus and in Denmark in general, his broad audience lectures. He's also very fond of new ideas, and he's very curious, which made him, which really pushed him into this quantum game project you might have played with some years ago, and also I think this is what led him into developing this quantum music project together with the Danish composer Kim Helweg. So again, correct me if I'm saying wrong things about you. So you started composing at the age of 13, and you published your first work at the age of 19. Your influences are very various. So including contemporary composers like John Cage and Penderecki, also classical composers like Beethoven you like to tickle a bit, if I understood well, but also jazz music. So you like to explore well, all sorts of forms, and also different ways of performing. Which means that you like to collaborate with choreographers, for instance. So your music is played all over the world, Asia, Europe and America. And you collaborate a lot with the Royal Danish Ballet and Orchestra. And also with Klaus, so which leads me back to the subject of today's lecture. So I'm very happy to let you talk now. So Klaus will start for half an hour, more or less, and then Kim. So thank you very much.
So it's a pleasure to be here. And let me just introduce myself. Thank you very much, Etienne, both for the introduction and also for inviting me and Kim to come here and present this quantum music project. I'm a professor at the University of Aarhus in Denmark, and as Etienne just said, my research areas are quantum physics and quantum technologies, and I have become associated with this quantum music project. It actually existed already. Kim had a collaboration with the Department of Musicology in Belgrade, and there were sound engineers, and there were musicians that based there, and there were also quantum physicists that half of the audience know about, because roughly half of this audience are people from a conference which is going on these days. And Vlatko Vedral, who comes from the same city, Belgrade, actually knew a lot of these people. So they started a quantum music project, and Kim invited me to join the Danish leg of that collaboration. And what I would like to do tonight, or is to tell you a little bit about the basics of also quantum physics. It's not everyone in this room who's a quantum physicist. At least I see so young people, they can hardly be quantum physicists already. So I'll tell you a little bit about the physics of music and the music that we find in quantum physics, and also how it inspired us to the quantum music project. So the outline is that I talk a little bit about classical physics and how music can be described by a physicist. It doesn't become more beautiful music but it becomes the way we understand what is going on. What you see here is a picture of Pythagoras, known as a mathematician and philosopher. He is one of the first philosophers who described the mathematics of sound. Then I'll move on and tell you what is quantum physics, what are the ingredients in quantum physics, and I will try to convince you that music surely played a big role in the understanding and development of quantum physics. And then in the end, I'll talk about the quantum vibes, how we can see music instruments actually as very similar to the atoms that we study in the laboratories, while the music instruments is, of course, something that you are studying when you go to concerts. So the classical music, the science and music in the classical era. So Pythagoras is very well known for mathematical relation about the sides of a triangle. But he's also very well known for observations about sound. So there's this board of strings, and you can pitch a sound. And then if you actually put some block, so you play on only half of the string, then you get something that sounds very nice together with the other string. And these harmonies that you find if you play on half the string, 1/3 of the string, 1/4 of the string, was something Pythagoras loved. He was actually a little bit obsessed by the simple mathematical rules, and he had a claim that the whole world is governed by numbers. He also thought that the different planets around the sun probably were in proportion to integer numbers. They simply had to be at certain distances, 4, 5, 6, and 7 from the sun, because that would be a beautiful solar system. Now, we don't believe in that anymore, but the string thing I will actually return to shortly. Ptolemaios, maybe the best or biggest astronomer that ever lived nearly 2,000 years ago, is very famous for finding lots and lots of stars, thousands of them. And in fact, his observations were not observed any better until about 1,400 years later. But apart from his interest in stars, he actually also made a music theory. And he developed an explanation for some of the problems with the creation of harmonies, which actually stands to this very day. So physicists have always been interested in the music and sounds and harmonies, also because there's actually a physical mechanism behind the creation of sound, and the propagation of sound is, of course, also physics. So we are also obliged, we even get our salaries for understanding what is sound and this kind of phenomenon. I'll tell you a little bit about classical mechanics. This is Isaac Newton. Based on observation of the planets, Isaac Newton came up with the fact that all this planetary motion you see if you look into space is not just God's will, and it's also not because the planets have a certain desire to move around in these circles. They actually all follow one simple formula, and that formula is Newton's second law. It says that there's a force, and if there's a force, there's a consequence on the motion. The force is the gravitational force that pulls everything towards the star here, and that means if you try to move straight ahead, because of that force, your orbit will be bent. And if you solve Newton's equations, you can understand the planetary motion of all the planets. And that really kicked off modern physics, modern theoretical physics. Now we have formulas and we can calculate almost everything. The gravitational force, as I told you, holds the planets in orbits, and it's also the force that makes things drop on the floor. There's a famous story about Newton discovering gravity because there was an apple that fell from a tree in his garden, and he realized that that's actually the same thing as when these planets are moving around. Now, this is very simple classical mechanics. Now I'll move to something which is a little bit harder classical mechanics. So a little bit harder classical mechanics is if you have a complex object. So this is like a rope or a string, and if you pull in both ends of such a string, the motion is going to be very complicated. It's kind of wavy motion you see here, but it's all described by Newton's laws. So in fact, if I look at a little piece of that string, then the ends of the rope pulling here, because they are pulling a little bit downwards here, if the string is bent up like that, then the pull will actually also pull it down. So the force here is going to pull this thing down. And that is actually what makes the violin string or the guitar string vibrate up and down. And if you want to solve the equation for that, then of course you have to realize that the whole thing is moving at the same time, and it can all look very complicated. But we can solve these equations. And it's no longer true, as Pythagoras said, that numbers rule the world. It's actually Newton's equation that rules the world. It is the force forcing this motion to occur that tells why this string is moving the way it does, and we can solve those equations. And what does happen when we solve these equations is the nice thing. That is that this string will have, for example, a simple motion where it just goes up and down, and that is one particular frequency. But if you make a string which is shorter, half the length, it will also move up and down, but twice as fast. So the kind of observation that numbers matter and there's something magic going on is true, but it's not because there's something particular about the numbers. There's something that comes out when you solve these equations by Isaac Newton. So here's a guitar, and what is shown in this picture is somebody who has measured how the surface of the guitar is vibrating. So when you play the string is going up and down with a certain frequency. That's actually transmitted to the whole instrument. And when we are hearing the music, we don't hear the string move. We hear how the whole box is moving here. And the guitar works as a loudspeaker. I would have liked to show the violin, but I couldn't find a picture of the violin like this. What you see here is the guitar playing a deep tone. And what you see here is the guitar playing a higher pitch tone here. So I'll come back to that picture a little bit later. I'm very fortunate I don't have to solve the equations for this pattern, because this is a very complex body, but we can at least take a picture of it and see how nice it looks. If you take the skin of a drum or any of the instruments you see among the drum instruments in the orchestra, it's the whole surface who is vibrating up and down in nice patterns, and this is why you have a characteristic tone of that particular instrument, because frequency is the same as tone. If you take the organ pipes in the big organs, it's the air pressure inside the organ pipes who are changing up and down, high pressure, low pressure. And because there's a certain length of the instrument, these patterns of high pressure and low pressure have to match into the length of the instrument. And that's why you have the long organ pipes playing very, very deep sounds with slow motion of these pressure. And you have the small organ pipes who have smaller patterns, and they are vibrating faster, and they give you the higher tones coming out of the organ. And I hope you don't fear that physicists think that music is just about numbers and solving equations. We also think it sounds nice, but we are happy at the same time knowing also a little bit about what's going on inside the instrument. Now I'll tell you a little bit more about the strings, because this is a good way to introduce our quantum music project and also quantum physics actually. So here I show you what a string can do. It's attached in both ends of the violin, so you can have the string move only in the middle. But it can not only rotate or vibrate in that way, it can actually also vibrate in the figure 8. And if you have been doing rope skipping in the schoolyard as a child, you know that if you take the rope and you oscillate it twice as fast, then you see this figure 8 pattern instead. If you're fast enough, you can even make this pattern happen also in front of you. And if we solve the equations, this frequency at which it goes up and down is just half of that one, or this one is just twice that frequency. This one is just 3 times the first frequency. And higher patterns all come out regularly being at higher and higher frequencies with these regular intervals that Pythagoras admired so much. I don't play violin or guitar. I'm actually playing the clarinet myself. The clarinet, it's a pressure thing standing in this tube. It's open in one end and it's actually closed in the other end. So therefore you don't get the same condition on both sides. You get closed and open boundary conditions, as we say. It's possible to vibrate here and not in the other end. So here it's a different pattern. You can have this new pattern. This is 3 times longer than that one. This is 5 times longer than that one, or shorter in the wavelength pattern. And that actually means that the frequency is 3 times higher and 5 times higher. It means when I play the violin that there will be a second tone being played which is an octave higher for the musicians. While if you play the clarinet and you blow a little bit harder, then you will actually play this tone which is not an octave higher, but is the 5th tone in the next octave. So that makes the clarinet sound different from, for example, some of the other instruments. So this is a simple, basic idea about what is going on at a very simple level in the music instruments. Of course, we have built instruments where we can play many different tones. So this is a grand piano, and there's lots of strings, and the long strings can play the deep tones, and the short strings can play the high tones. And there is a whole sequence of particular tones we can play here. And this is, of course, just by hammering the key. When you play the violin, you have to put your finger on your string, and you can put it almost anywhere you like. But on the piano, you have to hit the keys, of course. And they are designed in such a way that there is a standard, which is often 440 oscillations per second, 440 hertz, which is this A, at which you tune your symphony orchestra. And then all the other frequencies can actually be calculated from that, because every step to the neighboring tone is adding 5.94% to the frequency. Okay, that's a funny number. But it's made to be like that, such that if you go 12 half tones, then you have exactly multiplied by 2. And that's an octave. And the reason that the octave sounds so nice is because when you play that key, you're hammering on a string, it plays that frequency, but the same string also has the figure 8 vibration, and that is twice as high. So when I go up and I hammer this key at the same time, it actually already has the sound present from the first key down here. The octave is already being played when you play a key on a piano. And so the octave is a very simple interval. It sounds almost like the same tone, except a little bit higher. The fifth tone, the interval from C to G here, that's the increasing the frequency by almost 3/2. So that's again one of these magic numbers. Okay, so here are the strings as I showed you before, and here I'm really going from 1 to 2 to 3. So this is really 3/2 of that one, or this one is really 3 times the frequency down here. It's very funny if you go on the piano, because if I actually look at this tone which is sitting here, it's not exactly 3 times the lower one. It is 2.996 times the lower one. And that's actually a mathematical wonder. So for the physicist in this room should appreciate a funny fact that if you have the division into 12 halftones, then if you go up to this one, you can get that close to the ratio 3:1. And that's because it's divided into 12 equal intervals. If you wanted to build a better piano, which gets closer to 3 than 2.996, you have to have 43 keys in an octave on your piano. So that's a funny thing. I mean, then we would need many fingers to completely appreciate playing on such a thing. That's no quantum yet. Sorry about that. We have to get to it. So now let me get to the quantum physics, because all of that is the classical physicist gradually understanding what is going on in music instruments, why they sound good, and how they play. But let me now move to this new physics, the quantum physics. And quantum physics, in a short description, is the explanation of something that people have actually seen always. Since we were Stone Age people, we have made fires, and when you look into the fire and the temperature cools down, the glows go from yellow or white down towards the red colors. And this change in color is actually what led to the birth of quantum theory in year 1900 by a German scientist, Max Planck. The distribution of colors that you see if you look at the sun, well, the best way to see it is actually to look at the rainbow when there is a rainbow in the sky. That's just the colors of the sun that have been split out so you can see the different colors in different directions. And if you take the sunlight and you split all the colors out, you get all these different colors from red all the way to blue. Now there's one thing that people saw already nearly 200 years ago, that is there are dark stripes in these patterns here. There's colors where the intensity is a little lower or a little bit higher. And these stripes are actually associated with the presence of material in the solar atmosphere. So for example, there are 2 orange stripes up here, and that orange stripe is the same color as the one you see when you drive your car on the highway. The orange lamps, they have sodium gas inside, and they shine light at exactly that color. It's kind of magic if you're an astronomer, that you can learn that this color is the same as that color, so there must be the same kind of atoms in the sun as we have on Earth. And there's 100,000 lines in this picture. And all these 100,000 lines we can recognize as atoms that we also have on Earth. And therefore we actually know that the sun atmosphere consists of the same atoms as we have on Earth. But I'm getting derailed because I think this is such an exciting story, but there are so many other exciting stories I should tell you. But there's one story I have to tell you. When people in the 1850s looked at these colors, there were some colors they couldn't recognize from anything ever seen on Earth. So they thought it was a special sun stuff, and they didn't know what that sun stuff was, so why not name it after the sun? And sun is helios in Greek, so they call it helium. So helium was actually discovered first in the sun, and then only 10 years later, people isolated helium gas here on Earth. You know why we don't see helium. I'm sure the kids know, because if you have a balloon with helium inside and you don't hold on to it, it flies away. So helium flies away from the Earth. So you have to be careful when you get your helium. So we're looking into the sky and we can see atoms. It's all very nice, and the astronomers are happy and they go away and do their observations. But as physicists, we want to know why. Why do atoms send out light? Why does sodium have exactly that orange color? Why does helium have exactly the color of helium? And the explanation to that is really what came in the early theory of the atoms. So I'm very proud as a Dane to show this theory, because it's the Danish physicist Niels Bohr who in 1913 explained why atoms send out the special light they do. He says that if you have a simple atom, here's a hydrogen atom, then it consists of a nucleus, and then the electron is like a planet in orbit around its own little sun, and that little sun is the atomic nucleus. That does actually not tell us why there's a special frequency, because this thing would send out light possibly with the same frequency as it is oscillating. In your smartphone, when you talk to somebody, you also make electrons go back and forth in a little electric circuit, and the frequency at which it goes, that's the frequency of the radiation by which you're talking on your smartphone to somebody. So the problem was that this model can actually have this electron go around faster if you move closer, and more slowly if you move further away, just like the satellites are moving slower the further you take them away from Earth, for example. So Bohr, he had to make some extra theory. It's not really theory, he was cheating, but don't tell anybody I told you. He was doing something that he called postulates. He just said, well, the electron is in orbit like a satellite, but it can only be in that orbit, or that orbit, or that orbit. Why? Why can it not be in between? Of course, he doesn't tell us. He just says you can only be in these orbits. And then he says, in fact, it does not even radiate when it is in the orbit, but sometimes it jumps from one orbit to the next one. That's called the quantum jumps. And when you jump, then suddenly you don't have the same energy as it takes to be here, but now you should suddenly only have the energy that you need to be in this orbit. And the difference between these two energies is released as light, and that light has a special energy, and that's the same as a special color. So Bohr, he really cheats. He makes builds a model in which he claims that light can only come with certain frequencies, can only come with certain colors, and then he builds the model so that it becomes the colors that we actually see. But he had a few tricks up his sleeves, and people were very convinced. This is a very interesting idea, that in atoms, the electrons can only have very special energies, and when you change your energy, you have to get rid of it, and that's the light we see with special colors. Or you can also shine light on this atom, and then you can make it jump out, and that's when we get the dark stripes in the spectrum from the sun. Now, it was not very good that Bohr only made postulates and not a real theory. So in the next couple of years, he was trying to extend this theory to other atoms, to helium and to bigger atoms, and he could make super nice drawings, but he couldn't calculate the colors. And people realized in the early 20s that Bohr's theory is wrong. So you heard me right, Bohr's theory is actually wrong. And we needed a new theory, and the first stimulus to that new theory came from a French physicist, Louis de Broglie. And Louis de Broglie, he said, instead of just postulating these orbits, could we have a mathematical principle who says what is special about this? So what about some kind of wavy zigzag pattern? And the only circular motion who is allowed is the one where this one bites its own tail when it has made it all the way around. So you can see I can have this one bite its own tail, but if I go out a little bit further, it will no longer bite its own tail. So this is de Broglie's hypothesis or idea that there should be a kind of wavy motion here. So de Broglie was also wrong, but he was less wrong than Bohr. So other physicists took over and said, okay, waves have mathematical descriptions. I told you already about the strings that are described by Newton's laws. Water waves on water surfaces have equations we can solve. The drum skin on a drum has an equation we can solve. So a scientist called Schrödinger, he took some of these equations we already knew, and then he saw if he could fit one of them to actually give the kind of solutions we're interested in. So that physicist, and I just remind you that this is a fantastic insight by de Broglie. He says, to explain why we have only the special frequencies, maybe it's a wave pattern. I'm sure he thought about the way music instruments play only at particular frequencies. I can take a little piece of material, a little stone, and I can oscillate it back and forth at any frequency. But if I take a string on a violin, I cannot make it oscillate back and forth at any frequency. It has a very select set of frequencies that it can oscillate with because it is this vibrating big object of a string. It has definite frequencies because it is an extended wavy-like motion. So waves like special frequencies. And so to get special frequencies out of the atom, why not install some wave motion inside the atom? So I'm sure that if de Broglie was not playing the violin, he probably saw one day and figured, oh yeah, there's a string here, maybe that's what we have, the violin string going around the atom. So here is Schrödinger, and for the pleasure of all of you, I put the equation that Schrödinger wrote down, 1925, publish his paper the next year. This is a mathematical equation, and we will not solve it here. We will not even discuss it anymore, but it's a complicated equation because it does describe something complicated. Even the water surface is complicated, of course, to describe by mathematics. But Schrödinger solved it, and when he solved it, he got lots of funny solutions. So these are the solutions for Schrödinger's equation for the atom of hydrogen. So these are pictures of something that we call the wave function, and all of these pictures are wavy type solutions, as you can imagine. And I love to make this little comparison. You see the guitar from before. So here are 2 areas. Here are 2 areas going up and down. Here are 6 areas, and over here are 6 areas going up and down. So the guitar vibration is actually a little bit like the electron wave function oscillations that you find in the hydrogen atom. And here we get special frequencies, over here we get special frequencies. So this is really a link between music instruments and atomic physics and molecular physics. So what is quantum music? Well, it's a way to take this formalism, this idea about atoms and how atoms work, and not only make it a physical wave thing, but take some of the phenomena and see if that can inspire composers and musicians to actually make music. And it's important for me to emphasize that I'm not ordering from my composer colleague, please play this kind of physics for me, or please play this kind of physics for me. That can also be fun. You can go on the internet and you can find many musicians who play quantum physical effects. But this is more about seeing what kind of physical phenomena can actually, when observed and listened to by the composer, inspire to interesting music. So it's an alliance of curiosity between the scientists and the musicians in this project. We try to avoid music illustrating physics phenomena, but actually more have this kind of collaboration. It's a product in the end because there's music coming out, which is coming into concerts, which is also a very exciting part of this. So we can play the atomic spectrum, and I'll just tell you a little bit on the technical side how we do that. We can also interact with real physical experiments. So we have physical laboratories where they're actually studying atomic systems. And you could imagine a music instrument who is connected to such a lab. And when you play on the instrument, then something happens in the lab and the sound can come back. We have not made that collaboration work yet, but we have the possibility and in several labs at my institute. So here's actually a cold atom lab, which is connected with the internet in such a way that anybody can play with that experiment. It's a BEC, Bose-Einstein condensate. We had 168 amateur teams building each their own condensate 1 hour over a full week campaign. Nobody were physicists, they were high school kids and amateurs, just getting access to the control of lasers and magnetic fields in this laboratory. And this is directly to be plugged into a music interface, and then we can play on Jacob's Bose-Einstein condensate. But let me come back to the atoms. How do the atoms sound? Well, they don't sound at all because it's light coming out of the atoms. And if you look at the light coming out of the atoms, it is oscillating at frequencies which are crazy, and you would never be able to hear those frequencies. So there's a little bit of translation where I take the optical frequencies of light, which means colors, which oscillate 100,000 billion times per second. Okay? And then we want to bring that down to a few hundred times per second or 1,000 times per second, where sound that you can hear is actually oscillating. But that's easy, that's just the number. So I just have to divide by a very big number, and then we get into the audible range. And that's exactly what we have done. So here you see the Serbian LP duo playing Kim's very, very nice music. And there's a mathematical formula. I already showed you this one several times. I said if you have a frequency, you can multiply by 1 or 2 or 3 or 4 or 5, and then you get the different frequencies of the string. Okay? We have a slightly more complicated formula over here. That's the formula for the hydrogen spectrum. It says you should take one number and another number, then you should take 1 divided by 1 squared minus 1 divided by the other 1 squared. Okay, this is a little bit more complicated, but not terribly complicated. And if I do that, then I can create lots of different frequencies. Well, let me skip that, because if either you can see it in a second, or you don't see it if I spend 5 minutes on it. Right? So, but there's a simple formula who tells us what are the frequencies of light, and that we can now translate into frequencies of sound. And this is exactly one of the pieces that Kim has made, is based on these numbers we get out of this particular thing. So we have particular frequencies, we can translate them and try to show where they're sitting as keys on your piano. And then you can suddenly play this second series, the Balmer series, or you can play the sixth series, which is going to sit somewhere else in your piano. And that's the tones you are then allowed to use when you play this music. So it's great fun to talk to the composer and give the raw numbers, and then Kim is putting it into his notebook and showing where is it actually sitting on sheet music paper. And I'm sure the musicians have also looked an extra time when they got this music to actually play. Now, there's a second step in this, and that's something that the physicists will know, that quantum physics is a really strange theory. It's governed by randomness. It's governed by something called collapse, the quantum jumps. So this is something that we have not installed in the music as of yet, but it's some of the things we are fighting. Is there a good way to actually use that in a creative process of making music, some of the weird quantum mechanics? So we're looking at this thing that there's a wave, but there's actually also a particle present. The wave particle is never really at rest, so there's nothing that is really quiet in our music, perhaps. It's never completely dark in quantum light. It's always something we call vacuum fluctuation. Empty space is not really empty. It's actually an inferno of particles and antiparticles that are coming and going all the time. All these elements that are completely familiar to physicists, which role do they actually play if you want to build music inspired by this kind of stuff? There's something we call entanglement and spooky action, teleportation. How do we actually get that into our music or into the brains of our musicians who will have to play this? And how does it sound to you and how does it sound to me? So a personal remark from my side, because my colleagues sometimes ask me, what do you get out of it, apart from having fun talking to musicians? For me, it's great fun to actually interact with people who are as professional as I am as a physicist. I'm talking to a composer, talking to musicians who are treating their job, of course, with the same serious attitude as I'm treating my job. So to actually have a serious discussion with musicians about this process is very giving. I also hope that some of this music can give me an intuition for new physics. As physicists, we're always thinking in images, which is pictures, but why don't we think more in sound? It's because we have to train it first and maybe systematize it a little bit. I will finish. This is my last slide before Kim will take over and tell you what it actually sounds like. Niels Bohr, I'm sure he would have loved quantum physics. He loved to speak in analogies, and he's famous for many quotes. Many people don't like him for his quotes, but here's a nice one. He said once that we must realize that when atoms are concerned, language can only be used in the same way as within poetry. Also, the poet is less bothered about describing facts than about creating images and establishing mental connections. Because quantum mechanics is so strange, so the words actually don't fit very well. But maybe we should just think about the words we use as physicists as if it's poetry. I think he would like quantum music. I think we can also say that when atoms are concerned, language can only be used in the same way as within music. Music is also less bothered about describing facts than about creating images and establishing mental connections. So with this, thank you very much. I'll pass the word to Kim.
It's a great pleasure for me to be here and to explain how I work with Klaus and how I approach the information from quantum mechanics and put it into music. First of all, I have to underline I'm not a physicist at all, so don't expect me to go into the details with that. First of all, I think this of composing. Composing is something where you include your experience about the world, and you see a lot of composers being inspired about the moon, the stars, and the universe, but very few being interested in this very small world that's inside us. So when I was asked, because the idea for this project came from Belgrade, because a musician and a sound engineer and a physicist went to the same school. And they were sitting in a bar, and they got the idea, why don't we try to put all these things together? Because no one had done this before. And the group was LP duo, that's Klaus mentioned before, a piano duo. And I have written a lot of pieces for them, and they asked, oh, couldn't you join us in this project? And I did, and it was a great inspiration. So I will take my starting point from this project, and then talk a little about the composition I made in the last 3 years, because this project started in 2015 and actually ended this year. And by the way, maybe I should say that what Klaus talked about and what I am talking about is going to be published in a journal in Belgrade. So if you're interested to read it, it's possible. So the project was called Quantum Music because it's also the idea of inventing an instrument, a hybrid instrument that can include the ideas from quantum mechanics. I was focused on the composition and how to approach this. And now this is a little bit chronological, what do you call this, the history of my approach to the project. So I will start with the information I got. First of all, there were made, Vlatko Vedral made a video, what he called quantum chapters. That's one of the most important events in quantum mechanics that could inspire for different works. And I can go to the next one here. That's just about the possibilities I was thinking about. You have the quantum information, it influences the music composition. You can do it in the structure. I will come back to that. You can do it in the tonality. That has very much to do with the frequencies that Klaus talked about, and you can do it with the rhythm. That's a kind of elements that you use when you compose, if you try to divide them. Of course, that is very, very difficult. Then you can think about the musical instruments. That's not of my business, but that's to build an instrument that is based on the information from quantum mechanics. And then the musical theory, which I think is very important because the knowledge about quantum mechanics can influence the approach to music and to music history. I have a few examples here. I mean, as you already saw and heard from Klaus, it's a way of understanding music also. And the next one. And here are some selected events from the quantum chapters. Vacuum, one particle, two and more particles, superposition, Bose-Einstein condensate, quantum leap frequencies, and probabilities. And I will go a little bit in details with this, because that's all something that you can think about when you compose music. Vacuum has to do with the silence. One particle could be the understanding of how you can construct music and melodies. Klaus made some beautiful drawings for me, where they became more and more interesting because sometimes they move that way and then they move the other way, like particles and antiparticles. And this, I think, is still bothering me because I don't know quite how to do with the information, but I think that information is so interesting that you can go backwards in time. How can you do that in music? And then there's a superposition, which actually is somehow is a picture of the LP duo. There's a piano duo, two musicians on the same instrument, two places, but can also be used in another way. And then the Bose-Einstein condensate, where I actually wrote a cello concerto based on the idea of a condensate. And then the quantum leap frequencies, which actually is very interesting. I will come back to that. That's something that where the quantum mechanics give information that can generate scales, musical scales that you can use for composition. That means instead of using minor or major, you can take one of the series of the frequencies and use as a music. And that's what I did in the last piece you hear today for two pianos. And then the probabilities is very interesting. I didn't work so much on this, but the probabilities is very new and another way of thinking of improvisation. A lot of people have this theory, oh, it is better to write music on score because then you can force yourself to develop something new. If you play as you wish, what you like, and you will repeat something that already happened. Probabilities is actually saying something that we expect something to happen, but we don't know what's being in the end, what is coming out of it. So this is could be a very interesting way of making music in the future, that the improvisation is included in scores, like probabilities. And that's something I for sure will work on in the future. The first thing I thought of was this, the quantum world is a very small world. The time difference between our world and that world is huge. So my first exercise or etude was to play with time. I'll come back to that. And that's of course the tempo. I took a very famous piano piece by Pierre, which is a very slow piece. It's called Fialina, if anyone knows this. It's a very, almost like a meditative piece. But then I took it and stretched it even more. It's already very slow. And then, when I did that, I certainly heard that there were new music created. So inside with the music we hear, there might be totally different music if we stretch it and listen to it. And that's how you can, can go in and hear sound particles. That's it's that you try to find the smallest unit in the music, in the sound. And that's what done with the time stretch. And just to say, now to connect with the music history, I don't know if you know, but John Cage actually made a piece that I think it takes like 400 years to perform. And I think that's it's a step on the way. And maybe we would hit the music that will last forever. And then the opposite, we have As Fast as Possible. Nancaro, the Mexican composer living in Mexico, he was writing for the player piano because the pianist couldn't play so fast as he wanted. So his music is extremely fast. You can almost not hear what's going on. And some of the notes are so quick, so they sound like one long note. So we are back, there's a combination, or there's a link between 4 and 5 here. And most of you, I think you also know Ligetis microtonal pieces, where they're also playing very fast notes. So that's given me a new way of thinking, of approaching. I mean, those composers didn't think that they did quantum mechanical or quantum music, but that's a way of thinking that has a connection for me. And then we come to the sound vacuum. Vacuum does not exist in quantum mechanics. There will always be something left in there. And that's actually also what the composer John Cage found out. 2 ways. He locked himself in a room where there was no sound at all, and then he started to hear something new. He could hear his blood and sounds from the body. And he also made this very famous experiment with the musical silence. Musical silence is when the music stops. And he said it does not exist because what the sounds that happens when you have this musical silence, like a general pause in the orchestra or whatever, there will still be a noise that you have to relate to. And John Cage thought this was music. But now we can also understand it is a way of expressing vacuum. You remove the music and then you have a musical vacuum, but there's still music there. And then here, where we have the kind of, with the particles that you can relate with the structure in music or notes. And then, as I told you before, the movement of a particle and an antiparticle, I think is very interesting, but this is for the future. And this is Bose-Einstein condensate cello concerto, where the basic idea was to have this kind of cooling down an orchestra. And I did it different ways. I took one group at the time. It was, first the winds, the brass and the strings, so they are actually getting to one instrument, and then in the end the orchestra is just swallowed up to being one big body somehow, and behaving the same way. And that's why it was a cello concerto, because a cello concerto is about a soloist sitting in front of the orchestra and being outside the orchestra. It's a kind of fight. But this fight is stopped. And so this is an example. We will here extract from this of just being inspired. I mean, the tonal material was not taken from quantum mechanics at all. Only a chord. I took a chord so that Klaus gave me the frequencies for the Bose-Einstein condensate frequencies, and I built a six notes chord. And that's the premiere of that piece. And superposition for two pianos is called superposition. It has nothing to do with so much with that we have the two pianos. Is the way of also constructing that there are all the material musically is in two places at the same time during the whole piece. And here also, as Klaus mentioned, we used the different series. I would show them, and I will call it transposition, because you just put it down octaves by octaves, and then you get so low that you can play it on an instrument. And when I made this piece, I had a long period where I just tried to taste the tonal quality of the piece. And it's very, I'll come back to this too also. It's very interesting because the scales are what we in musical theory would call atonal and tonal at the same time. So it's actually very modern, because all composers all over the world, they want to make music that is tonal and atonal at the same time, or none of them. And then we have the different state of the scale. That's also very important. Actually, it was a little bit difficult to have two pianos, because there's nothing like two pianos that are more classical. I mean, you have the scales, and then they're just fixed. It's not on a violin. And when you have all these frequencies, you would have notes that's a little bit too high, a little bit too low, and different other states. So the easiest way to make a use of this is, of course, electronical, where you can generate the frequencies exactly. The next step is a quarter note version. That means that you, instead of 12 notes in the octave, you have 24. That's used by a lot of contemporary composers, and also exists in a lot of ethnic music. And you have voices, strings instrument, winds and brass that can do that, but the piano can't. And then in the end we have the chromatic version, which is the classical instrument like the piano. And we have to adapt all the wrong notes so, to chromatical scale. Yes, and now to the sound. And I would just start with some of my early experiments with the vacuum. And I hope there would be some sound. That's the concert hall in the Royal Danish Academy of Music. No musician, but there are music. So you could save a lot of money if people like music like this. But it's actually in the room, in the space, this sound. Of course, there's some technicalities with the music program when you start to make it louder, where the noise can come from other places. But if you record any empty hall and put the sound up, you have some kind of noise. And it's maybe good for meditation and things like this. Then I want to, now with the real information from quantum mechanics, here is the big condensate chord. And I have marked the wrong notes a little bit, so they are making them what we call a kind of glissando, just to hear it. Information directly from the quantum world. And I mean, it sounds sometimes, there are some interesting pieces also, but when we go to the Balmer series, we can find out that the first intervals is the same as the theme from Richard Strauss, Till Eulenspiegel. And this is sounds actually as the chord, mysterious chord in Scriabin's poem, Poème Le Feu, I think it is, Prometheus. About them stealing the fire from the gods. So maybe some composers had the kind of idea of what was going on in the micro world. I don't know. Time is running, so I will go to that's my piece for LP Duo. And each piece is built on, here you see the frequencies for von Neumann transposed for music. And as you see, there are very few different notes here, so it's a, that's okay. So it's a little bit boring. But then again, you can stretch this, so you keep the relationship between the notes, but that you fill out the whole piano. And this I had to do with the Lyman series. But together with Klaus, we worked out a kind of list. It's here. Here, you have all this. This is first Lyman, Balmer, Parshin, bracket, Font, Humphrey, and then series 7, 8, 9. So you see there's a lot of material here. And that's the basic for my 9 pieces for the 2 pianos. So one for each series. And it's very interesting, but I don't talk about this because there seems to be a relationship between the series. Very close in relationship. And when we go to the first piece for the 2 pianos, you see here the well-known drawing. And here we see it in the notes. And you can see this same relationship. We have a big gap, less gap, less gap, less gap, and then it gets almost into a scale, and then it gets microtonal. So you can divide it in 3 parts, this with the chromatic, and now it's adjusted for the pianos, so you would have a lot of quarter notes in between. And here you have almost like a pentatonic scale, so sometimes it also sounds very ancient, you know, like folk music from old days. And then the funny thing, if you need a bass note or like the most important chord, it's not there, because when you go down here, it gets very dissonant in the bass line. So this is the bass notes we have here, and I would call this the melodic area, and then the microtonal area. And looking at the traditional slow. If you take the natural scales, you can say C. It has a little bit the same construction, besides it sounds much more harmonic for us. You see, only the C's are clean the whole way through. The rest is a kind of variations. That's what we find in the nature when we hear a note, a clear note. And you see the big gaps getting less, then it goes into a scale, and then it becomes microtonal in the end. Exactly the same as the series of the Lyman scale. Ah, yeah, I had to. Ja, tak for det. Now here we have LP Duo, and they're playing the scale you just saw. And what I did is the first piano there is playing the microtonal, so it sounds a little bit diffuse in the end, in the beginning. Then the other piano starts to play the middle section and going out like this. And when they finish the building up, and you can hear all the notes in the Lyman, then it's finished. So it's total built on this scale. And it also gives the kind of atmosphere that you find in this scale. I find somehow that it's very close to some impressionistic music. I mean, it has a kind of it doesn't have this kind of classical solution in it, but it's a kind of more floating. So this piece is only built on the Lyman series. I have to say, and the lights we also developed, so this is also connected to the scales. So yeah, this was only a short introduction. I wanted to conclude also, which is very important. I mean, of course, the composer has a kind of style when he or she is composing, and this material can be used. You know, the tone rows can be used in any kind of music, jazz music, rock music, and it has no limitation. So it's actually just another way of approaching music and musical scales that can be used, come out of this. And now I'm working very hard on this, of trying to make a piano sonata where the piano is playing forwards and backwards like particles, and this is quite interesting work, but it's a work in progress, so yeah, that's what I used my last 3 years for. Thank you.
So are there questions? No? Oui, yeah.
Sure. Just a practical question, doesn't matter. Do you have anywhere online where we could see the entirety of this piece, or is there a link to it?
Not yet, no. But that will come, and then you just, if you write superposition, but if you write quantum music, you can, a lot of the material we have showed today is there on the internet. Okay. Also the about the quantum chapters, but it will be there soon, I think.
So just search quantum music.
Yeah.
Was it hard to get all those microtones into the pianos? Why was it important to write music for acoustic instruments?
Why?
Why was it important to write the music for acoustic instruments? It must have been very hard to tune in all those microtones.
Yeah, that's what I thought was interesting, because it was so difficult. Because, I mean, when you work with electronic, you can do everything.
Yeah.
But you can't do that, and I think it's very important, I mean, as a composer, that the instruments that has a long history also, you know, follows the history. So for me now is to construct and work with an acoustic piano that can play backwards in time and forwards in time, and do a lot of interesting things that already exist. Piano called this piano that's Yamaha produced, that can be connected to a computer where you actually can do this stuff, but it also needs some software to do it.
Do you need
yeah, that's fine. Have you thought about making an instrument based on one of these series?
Yeah, actually, and Klaus is also involved in this, where you use also the overtones from the series.
Because I can imagine that, you know, if there are less keys in between. You know,
Yeah, actually, yeah.
You,
but strange keys.
yeah.
But you know, there are piano, because there are a lot of pieces with the quarter notes included in the repertoire actually now. So a piano tuner can actually go in and make this. Oh, now I make a tune it like a Lyman or Mølmer.
So I know you don't need the microphone.
So in particular, if you're going into these Mølmer, Passion, Lyman type of series, couldn't you also think of simply using a harpsichord and then really some squadra pura, since it's just on one scale, where you really then move the notes so that they fit almost perfectly into this overtone type of series?
Yes.
Because I think equal temperament, like we have it on our modern pianos, is totally useless for this type of music. And anyway, it's a cruel approximation to the tuning systems that were around in the ancient times or Baroque times. So why not just use this type of tuning system and really go for a harpsichord that really displays the Passion or Lyman or Mølmer type of series almost perfectly, and put the effort into the tuning, which you can do by electronic means these days,
Yeah.
and supervise it.
Well, that's a good idea. Very good idea.
Thanks.
I'm very honored, and I have a bunch of highlights for you. When we're looking in France or elsewhere on YouTube, you have the Brandy Aran series of videos, which are made with the Nottingham University, with the Prof. Sir Martin Polyakov,
Yeah.
and they are dealing with interesting stuff about chemistry. And recently we have named on the periodic table of elements new elements, including super EV elements. And we know that in the structures of these atoms, we have odd behaviors which are dealing about intrication in quantum theories, which are explaining the oddities of these extra heavy elements. We're now looking about a new island of stability, and lots of research are made in Dubnia or in another place of research in France or Russia or USA or elsewhere. And interesting things about your current works. I think that maybe there is an opportunity for you to use sympathetic strings. You know what it is? It is dealing about ancient instruments which are used in folks, including hurdy-gurdy. And because we have some transition effects with superpositing effects, maybe the use of multiple strings could be useful for you.
Yeah, for sure. But still, I think it's very interesting because actually there's a little bit like a philosophy. We see the quantum world from the classical world. I mean, we cannot be quantum. So for me, it's also interesting that we have this resistance or this crash between different informations. Yeah. So for me, it's also a kind of a world that can be added to the classical instruments.
I think that one other tool that could be especially useful for you is dealing about the Segre diagram, which is dealing about the stability or radioactivity of several isotopes. And it is possible to display this table, which is highly complex, more than 3,000 cases. And it is possible to display it with several false color scales. But I will show you to
yeah, please,
on my
please. Thanks.
Just a simple question. When we leave behind the tyranny of the 12 notes, well-tempered clavier, and go to something like the Lyman series as a scale, what happens to chords progressions, counterpoints? Have they been developed?
Sorry, the... Things like
chords.
Chords?
When you're playing two or more notes.
No, I mean, the music piece here, I didn't think so much about chords because for me the melody and the harmony was the same.
Okay.
You understand? When when you put the scale and then you put notes, then you have the chord, so it's actually only one chord that is the scale. I did there. But it could be really interesting. There's something, for instance, transposition between the different series and putting a chord structure. But from the scales here, you can see there would be, what do you call this in suspended accords, a lot of them. And there would be some few clean, minor and major, very few. Maybe with a little, unclean.
Okay. How much of this is known? I mean, just from exploring it, playing around with it.
How much is known?
Yeah, I mean, do we have analogues of the perfect fifth?
Yeah.
Or good chord sounds just coming from, say, the Lyman series tuning?
I mean, we didn't go further with this, with the tuning, so that's something we have to work on.
If I may add, so we have this collaboration with the sound engineer here also, and we actually want the musicians to help even build the instrument. As I told you, the difference between the clarinet and the saxophone is that the first overtone is actually the fifth in the next octave. The sax, it's the octave. So and they sound like different instruments. And that's of course a choice. If we take the tones coming out of the quantum scale, how do we actually want them to be balanced with respect to each other. Which ones are being played when you play the deeper one together with the deeper one?
Yeah, exactly.
And that's something that I think would be a super funny iterative process with the musicians. So we simply sit them down with the electronic instrument and let them play until we have this sound, which is going to be characteristic. So you can imagine several hydrogen atom instruments, depending on how they actually balance the overtone from the Lyman Alpha series when you play the piece. And that's like the real instruments also sound different.
You probably need a few beers for the musicians as well.
We use that as our favorite day.
So there are no more questions. I think we can thank again Kim and Klaus for this very inspiring talk.